Boom. Hello and welcome back to Precalculus1, section 3.2, Logarithmic Function. All right. Confirmed. Now, before we go into logarithmic function and all that kind of stuff, let's first talk some computation, go all the way back to the beginning. What is 2 plus 3? Anyone? Yeah, the enthusiasm is there. Nice. Now, if I want to retrieve either 2 or 3 from this calculation, I should write 5 minus 3 is 2, or 5 minus 2 is 3. So we see that there is this grouping between positive and negative, where negative minus sign of subtraction is the opposite operation, which undoes addition. And I am able to retrieve both of these input members, right, if I use subtraction. Here's 2 and here's 3. Now we have the same thing, obviously, for multiplication. 2 times 3 is 6. And then if I divide 6 by 3, I get 2. And if I divide 6 by 2, I get... So we see the same correspondence between multiplication and division. Division undoes multiplication. And I am able to retrieve both of the members, right, both of the factors, by dividing. Great. So now we see that addition works, multiplication, which is repeated addition, and now we have the uber fast repeated addition, which is repeated multiplication, which is exponents. So how much is 2 cubed? 8. And now I want to retrieve 2 and 3. So what's the cube root of 8? 2. We know that from intermediate algebra. Cube root of 8 is 2, because 2 times 2 times 2, 3 times is 8. How do I retrieve 3? I mean, you can't do square root of 8, because square root of 8 is 2 root 2. Has nothing to do with 3. So, yeah. It is log base 2 of 8, and we get 3. So what is log in the end? It's a mathematical operation. It's a mathematical operation done between two numbers to get a third number. It's no different than subtraction or multiplication or exponents. It's just, it kind of has letters in it, so, right? It looks weird. But it's mathematical operation. You learned at some point in life that 2 plus 3 is 5. You learned at some point in life that 6 divided by 3 is 2. You learned at some point in life that cube root of 8 is 2. Well, we are going to complete the set of basic mathematical operations, including the log. And how unfortunate for the log to have letters, right? It would be much nicer if it was like 2 heart 8 or something like that. You know, gives a 3, and then people would not be discriminating so much. So be nice, okay? Don't discriminate. It is a mathematical operation that is equal to all other mathematical operations. So have some decency, okay? Fair? Be decent people. So we are learning today about this mathematical operation called log. And as I said, you are going to use the log in conjunction to two numbers to calculate the third number. And it belongs, the log belongs to the set of mathematical operations. So now, when you look at the first and the last line, you see a relationship between exponential functions and logs, which gives rise to the most important formula in chapter 3, which is conversion between exponential and logarithmic form, because they're inverses of each other. So the most important formula for chapter 3 is conversion. A to the b equals c converts to log a of c is b. This thing, put it on a cloud, is going to be the most important formula of the entire chapter. We're going to have 10 formulas here, right, in a chapter, maybe more. This stands out as the most important thing you're going to see in chapter 3. Now, this necessarily tells you how we compute logs. Now, on your calculator, right, your TI 80 blah, or whatever else you have, you are going to have LOG button. And you're also going to have LN button. We'll see what LN is exactly today. So both of those are logs of some form, and you can use them to calculate stuff. So when you take your calculator out, if you have one, you can see the LOG and LN buttons on the left-hand side over here, about where numbers 7 and 4 are. That's where they are. Now, your calculators on the cell phone should have something. When you flip the calculator sideways like this, it opens up more options. Even Apple can do this. So you will see ln and log somewhere on the list. In the Droid case, it's right here where my finger is. If you have the other stuff, then the garbage somewhere else. All right. So now, we input two numbers in a log, and the output is whatever number we get. Now, the trick is that your calculators are limited to work only with two bases. You see that over here I have a base of 2. Your calculator doesn't speak base 2. So we need a formula that will convert the log into the logs that calculators understand. So there are certain calculators, very few, that would actually do log of any base, but people who design calculators usually don't bother to design that portion, because in sciences you only run into two bases technically. You run into base 10 and a base E, which is the special number we talked about last class. So, and because of those two bases are taking about 99% of application and everything else in sciences, people don't bother programming calculators to compute log base 2 of 8 because it's unnecessary. But then in math classes you run into these kind of logs. So you want to know how to do those, and we have a conversion of base, change of base formula, which will help you go into the logs that we need. And we'll talk more about that. But before I do any of those calculations, I want to make sure you guys understand how these logs work. So if I have 3 to the 4th is equal to 81, right? That's a calculation that you do in your head. 3 times 3 is 9, times 3 is 27, times 3 is 81. Or you can just say 3 to the 4th is 3 squared times 3 squared, which is 9 times 9, which is 81. Whatever way you come up with 81. When you convert this log base 3 of 81 is 4. So you see that it computes exponents, right? Now, this is the portion that goes on that no calculator part of the exam, computing logs. So let's say you have to compute a log base 5 of 125. That's the question. Well, in this case, we're lucky that we have these nice numbers. I can convert this, right? I'm going to replace this question mark now with, let's say, x or whatever. And when I do the conversion, I get 5 to the x to be 125. Now, can I write 125 as a base 5 somehow? Anyone? Can I write number 125 as a base 5 with some exponent on it? So what's the exponent? Yes, cube, 3. There we go. And now, you quickly see that x is 3, which means that log 5 of 125 is 3, because you just computed x. So yeah, it's a really long way around to compute logs. Not as easy as, 17 plus 7 is 24. You have to chase it a little bit. How about log base 10 of 10,000? What would you convert this into? Ten to the x equals 10,000. And now, how do I write 10,000? How do I write 10,000? With a 4. You have 4 zeros. So what's x? And that means log 10 of 10,000 is 4. Computing logs is not easy at all. As soon as I give you a problem that you can't do these exponential tricks where they don't match, it's game over. You have to use calculator or some other witchcraft to figure it out. If I go and I say log base 4 of 36, well, we can just cry about this. Because if I write 4 to the x equals 36, I can't write 36 as 4 to something over here. Because powers of 4 are 4 to the 1, 4 squared, and then 4 cubed, and then 4 to the 4, but you already see that 36 is in between these two numbers. This was x equals 2, this was x equals 3. So we know that the answer is 2 point something over here, but what? Right? So you can't compute by hand anything you want for logs. For exponents, you can. If you're on a desert island, you have a stick and you sand, and you want to compute some exponent, you just sit down and you start cranking it out. But for logs, can't do it. So what do I do to solve this problem? Well, before calculators, which are, by the way, about 40 years old or something, before that, engineers used slide rules And there were also books called log tables. So you get to walk around with the book, and then when you see log 4 of 36, you get to flip through the book and find the page on which log 4 of 36 is equal to 2 point blah blah blah. Today you get to punch numbers in the calculator. But just 50 years ago, you get to walk around with a book, because there were no calculators to compute these things. Now, I already told you that you can't put this in a calculator because it's a base 4. Your calculator speaks 2 bases only. There is the LOG, which is base 10, and there is LN, which is base E. So we need to learn change of base formula so you can use your calculator to compute logs. So again, problem like this and the problems above, they go on the no calculator part of the exam, because you can do this. This problem and similar stuff goes on the calculator part, which makes sure that you can use the change of the know how to use change of base formula. Change of base formula says the following. If you have log base A of B, you can calculate log of B divided by log of A, or ln of B over ln of A. You can use any of the buttons. So this formula you learn specifically to be able to use calculator. So now, what do I do with my log base 4 of 36? So I know that I need to get 2 point something if I do this correctly. Well, looking at my formula up here, it is going to be log 36 divided by log 4, or ln 36 over ln 4. Pick whatever you want. Do not mix log and ln. So it's either all log or all ln. And make sure you close the parenthesis after you type in 36. Otherwise, severe mistakes occur. So use your calculators. And if you are using intermediate steps, if you can't punch everything in at once, keep at least 4 decimals rounded up or right properly. So use your calculator. If you don't have a calculator, use your cell phone. It's okay. Just make sure that you are punching in both ln's or both logs. Close the parenthesis after 36. It's very important. So you go log 36, close parenthesis, divide by log 4, close parenthesis. Four decimals. Yeah, so 2 point and then put 4 decimals down. So I hope that your answer was log 436 is equal to 2 point 5850. Because you have 4, 9, 6. 6 makes 9 to go by 1 up, and then that one moves the 5 up. So 4 decimal places rounded properly. And we are going to leave this standard in quotation marks of 4 decimal places through the entire chapter. Okay? So chapter 3, 4 decimal places. Cool? Unless we talk about the money, you get 2 decimal places then, right? Because it's cents. 67 cents or 35 cents. But, so you don't need to keep 4 decimal for cents, but everything else 4 decimals. All right. Yes. Whatever you want. Try it. You have to get the same answer, which is why I put or. All right. So now we hopefully understand at least a little bit of how to, well, let's compute another one. So log base 7 of 1344. Another one. Another one. What do we get for the first one? 1. What do we get for the second one? 0. I call these cute rules. Here they are in red. Log A of A is always 1. If the numbers are the same, it's always 1. So what's log 10 of 10? What's log E of E? 1. What's log pi of pi? Right? So if the base and the number match, the answer is 1. The one on the bottom, log any base of 1 is always 0. How much is log 3 of 1? Log 10 of 1? Log pi of 1, right? So if this thing over here is 1, you can have A, any base, right? A. So log of any base of 1 is 0. And I call those cute rules. So guys, we have 4 formulas so far. Do we? Right? Maybe I should keep track of those formulas on the board, so you can see all of them at all times. So I'm going to write 4 formulas so far. We'll have more. Conversion. A raised to B is C, converts into log base A of C is B. That's the conversion. Change of base. Log A of B is log B over log A, or ln B over ln A. I still have to talk about what this means, but you know the formula. And two cute formulas so far. Log A of A is always 1, and log any base of 1 is always 0. The hell is in this thing? I have a headache now. No, this one is really bad. Try it. Right? I know. You know, keep it there. Keep it there. There's a reason why I throw it away. All right. So now, let's take a look at what are these special ones, the log, right? What is the meaning of log as a button? Well, log A means log base 10 of A. So it's just a lazy notation, okay? If you see a log without base, it is 10. This is not the first time in mathematics you know this, right? What is the meaning of this? Three times 5. I never said times over here, right? I just put, or even if I write it this way, right? I never wrote times. I can write 3 times 5 or 3 times 5, but I also have this notation where there's nothing here. And you know that if you are talking about mathematical operations and there is nothing in between two terms, it's multiplication, right? Well, now for logs, you need to memorize and learn that if there is no base, it's 10. We use this lazy notation because most of the bases in sciences are base 10. And metric system is base 10, right? But then you are going to see pH calculations in chemistry. They are going to have log base 10. You are going to compute stuff in physics for waves and things, so intensity of the sound, the decibel scale level, and earthquakes, and all of these kind of things. They are going to have log base 10. So a lot of applications in physics and chemistry have a log base 10, and because we are lazy to write the same thing over and over again, it's so special, we just said, let's keep writing those two characters. We are just going to make it mandatory for humanity to learn that if there is no base, base is 10. Very simple. The second one is ln, natural logarithm. So ln of A means log base E of A. That's what it means. Again, it's a lazy notation. It's special because a lot of our applications are using base E, which is a natural number. Mathematician Leonhard Euler was the one who came up with that and calculated that number and gave definition of that number, which you learn in calculus. That constant is about 2.7, all right? But now, when you look at this base E, right, ln is just a lazy notation. Guys, in both of these cases, what we actually use is 2 characters shorter to write than what it actually means, right? So 1, 2, 3, 1, 2, 3, 4, 5. So 2 characters shorter, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. 2 characters shorter, right? So I label them as lazy notations, and it is across the board on the planet. We agreed that's what it means. So now on your calculator, you see that your calculator can only compute base 10 and base E, because you have LOG button and you have LN button. So that means that you can compute ln of 7, like this. You push ln, you push 7, and you're done. Let's go. ln of 7. You just use your calculator, you push ln 7, and you're done. What do you get? 1.9459. That's ln 7. How about LOG 10,000? What's LOG of 10,000? Why? Why is it 4? Because, yeah, because life. Right? You see that? We did it by hand. We know how to do it without a calculator because that one was easy. But then you can just punch LOG 10,000, you will get 4. Because remember, this part, log 10, is just LOG button on your calculator. That's what the LOG is. Log base 10. And then you just type in 10,000. So you can compute all of these things. Nice. We are finally done with basic computation and basic formulas that concern the log and log calculations. Now, if you are trying to observe, maybe I should add these, I don't know, put green or red or something. Oh my God. Oh, coffee. Ah. No, I'm not. It's just headache. All right. So now we also said that log of A means log 10A, and ln A is log base E of A.
No, ln.
Yeah, ln A is log base E. All right. So we're done. That's the basic stuff. Obviously, you sit down, you learn it, and then you are able to compute anything. It's time. So far was arithmetic, right? Computing. Now we're moving to precalculus. Let's learn about logarithmic function. Okay, so far in the first part of this lecture, we technically did 2 plus 2 is 4, 3 times 8 is 24, right? So basic calculations with logs. Take two numbers in a log and what do you get? Now we are going to upgrade that idea into a function. You know that 2 plus 3 is 5. What you can do is you can make this into a function by replacing 2 or 3 by x. So if you say x plus 3, well, now that's a function. If you plug in 2, you will get 5. But you can plug anything else and get different values. So you get to upgrade your calculations from arithmetic into functions by plugging in a variable for one of the numbers that you used to know. So now we're going to do the same thing for our log. What I'm going to do is I'm going to say, well, you know, I have this log 2 of 8, and I got 3 on the other end. So what happens if I just go log 2 of x? Like, what happens then? Well, you just got a function. Because this x will be changing values, which would be giving us different y values, and you got yourself a function. So the general, it's not a formula, it's just a general form of logarithmic function is log base a of x. And then you pick what base, right? Base 2, base e for ln, or whatever. Now, the clock actually works in this room? Wow. Actually, I have it here, 4:33, so we're good. So let's take a look now at logarithmic function. We see that logarithmic function is really tough on computing. We have to use calculator most of the time, right? So it's not as easy to obtain the, x, y, and numbers and so on. But we also have the conversion formula. And if you are careful enough with the conversion formula, you learn exactly what the log is and how the log function, what the log function is. And what it is the inverse of exponential function. You see, if you write y equals e to the x, let's go with a, any base, a to the x. And you go and you swap domain and range, which is what you learned in your chapter 1, that to get the inverse, you swap x and y to get inverse. You see that now you need to solve for y. We use conversion, and the conversion says that the log a of x is y. Oh, I got a function out of this. So now you remember how what the e to the x graph looks like, right? You remember that, hopefully. You remember that e to the x graph looked like this, going through 1. Then again, because of the class prep and everything else you did, you've seen that the inverses are part. You went back to 1.7. You read about inverses. And you know that the inverse will give you the reflection on y equal x line. Which means that the log function, since this is our a to the x, our log function has to look like this. It has to be symmetrical on the y equal x line, and this is log a of x. So now we see, we derived how the basic graph looks like without computing points. We know what it looks like without computing points because we use the inverse of exponential, and then the graphical trick which shows the reflection. So now, graph of log function, I mean logarithmic function, but there are way too many letters to spell it. The graph of logarithmic function looks like this. Now this is what you must memorize. You memorized how, what the x squared looks like. You memorized what x cubed looks like, square root of x and 1 over x. You memorized all of those basics. You memorized what e to the x looks like, or a to the x, exponential ones. Well, now, and this is the last one you are memorizing in Precalc 1, you have to memorize the basic ln or log graph. That's it. Now, you might ask, well, does this go like this or like that? Again, not humanly possible to do a great job there unless you're going to compute points, plot those points, and trace which way it goes. I will tell you that you can have any of these situations like this, and that depends on value of a, right? You have log base a of x. So this value a will control which one of these you get. But again, it's not humanly possible to keep track of that perfectly, so we just draw a function like this in general, and what's important is that it goes through 1. Now we answer those important questions: domain, range, intercepts, asymptotes, all of that stuff. You need to know that. All of that is on your lab. And by the way, if you're splitting the lab, time to stop doing that. If you're splitting the problems. Because one problem on the next lab is going to address asymptotes and everything for exponential, and a different problem is going to be addressing the same stuff for logarithmic. If you split the problems, and you are not the one doing the log one, well, then you don't know it. You have to do every single problem on your own. And then when we have lab time in the class, you bring it in, and you show your answers to all questions, and everyone else in the group shows answers to all questions. And you discuss which one is the best, or all of them are the same, and you write the master plan, master plan. All right. What's the domain? Look at the picture. Negative infinity for domain? I don't see anything over here. Okay. Now, do I include 0? Do I exclude 0? Parentheses. Good. 0 is not included because it is not going to touch y-axis ever. And that's where x is equal to 0, right? So, all right, how about range? Beautiful. Negative infinity to infinity, you see that on y values starts all the way at negative infinity, and this part of the graph will always go up. So it's going to positive infinity. Great. How about x-intercepts? 1, 0, it's a point. How about y-intercept? Very good. Do we have any vertical asymptotes? Do what? Yes, what's the equation for y-axis? Very good. Very good. Do we have horizontal asymptotes? Okay. Do we have slant asymptotes? No. Good. There's your comprehensive list of things about the basic ln graph. Now let's use the lab from the group that's not here to go this again. Domain. The way you read the domain is you cover the entire function. That's not going to work here. You cover the entire function and you start sliding it to the right. Eventually you uncover, right? See nothing, 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 and whoop, there it is. Right, starts here. I should use so nothing, 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 and then there it is. It starts. So at 0, you see, I went. X is negative infinity, nothing, negative 3, nothing, negative 2, nothing, negative 1, nothing. X equals 0. It starts. So x equals 0, it starts, and then there is a function, there is function, there is function, there is function, there is function, and forever. So 0 to infinity. For range, same thing, start from the bottom. Immediately there is function. So that means negative infinity exists always, exists always, and boom. To positive infinity, because this will always go on. So, come. X-intercept, move your eyes. Y-intercept, well, it doesn't cross y-axis, so it can't have y-intercept. Vertical asymptote, which is the reason why we don't have y-intercept because there's a vertical asymptote there. And none of these two things, right? This is going to go forever and ever, and no horizontal asymptotes anymore. Great. These are the basic features. Now we need to shift and move and reflect and do all of those cool things from 1.6. I promise that 1.6 will never go away. So apply 1.6. Transformations. Great. Y equals log of 3 on x plus 2. Looking at the formula, what kind of a shift is this? X plus 2. Very good. Left-legged. Left 2 units. Nice. So, what do the graph looks like? We graph the original function first. I do that dashed through 1. 2 units to the left. That means that the vertical asymptote that used to be at 0 is shifting to -2, and the x-intercept is shifting to the left 2 units. So now I have same shape, except it's shifted. Observe that we gained y-intercept because it was shifted to the left. Next example. Y equals log 5 of x minus 2. What's happening here? What? 2 down. You see over here, plus 2 was grouped with x. As a contrast, it is the entire, oh, maybe the issue is that, okay, let's, before we do this, let's enrich our PEMDAS into PELMDAS. First of all, before I enrich it, let me write it this way. So I write PEMDAS this way because multiplication and division are of the same weight, same priority, and when you are computing in basic algebra, you do whatever is first to the left. So if it's multiplication, you do multiplication. If it's division, you do division. And same for addition, subtraction. Whatever is first as you read left to right. Now, logs are exponential, inverse of exponentials, so they fall over here, and also roots fall under the same roof. I'm not sure why is that not. There we go. So this is a square root over here, or whatever root. Maybe I can write it as the nth root. So now your PELMDAS, right, which is L, it stands for logs. So now when you are comparing this to your PELMDAS now, this is your L, and this is the subtraction S. So you see that this x, you cannot shift to the right because this -2 applies after the log does whatever needs to be done to x. So this way is shift right 2. This way is shift down 2. One more time. Shift right, shift down, shift right, shift down. It's like the eye exam. Shift right, shift down. And then use the PELMDAS to make it clearer, I guess. So now, to graph this, I will do the default graph that goes through 1 on x-axis, and my job is to shift everything 2 units down, so that 1 that used to be on x-axis is going to be 2 units below, and I have to label that. I mean, if you don't want full credit, don't worry about it. And now draw the same thing, except it goes through this point 2 units down. I have a minute and a half. Let's work on one of the reflections. Y equals negative log base 3 of x plus 2. What do I have in terms of transformation or transformations? Reflection on x-axis. And what else do I have? We have left 2. So if this value modifies x directly, which means in parentheses, it's left-right. If there are no parentheses, then it modifies the whole thing, and it's up and down. So now, to graph this, and I told you guys, reflections first, every time, reflections first. So we start with our basic default state that goes through 1. Reflect on x-axis. I'll do the next stage maybe red. So this one over here is log 3x. This one is minus log 3x. And then the final step is left 2. And that's the final graph. So the black line dashed is the default state, the one that you have to memorize, the shape of the graph, the basic shape. And then we have a reflection on x-axis because minus was applied to the entire thing. And then you have the, so that was reflection, and then we move everything to the left 2 units because of plus 2 within parentheses. When it's within parentheses, left and right. Next class, more logs. And then the following, more logs. And then finally word problems in 3-5, and chapter is done. See you all in 5 days. Whole bunch of homework to be done. This class is not over until December 10th or whatever, or 18th. So don't be taking a vacation, the after-test vacation. You too. That doesn't exist. See you all in 5 days. Do homework.